Hello and welcome to my presentation, Distributed Systems, Lessons Learned Designing Efficient Client Protocol. My name is Ihsan Demir. I am an open source developer. Have been involved in developing open client server protocol since 2016. And I have been heavily working on distributed environments, developing clients for Java and C++ languages mostly. And I like to do contribution to the open source projects. Today I'm going to share my experiences designing and developing these open protocols and problems and strategies we followed during the way. First of all, I want to give some information about the distributed product we have and the environment. So we have in-memory database that's distributed in a number of servers. We call it a cluster. And our clients access these database remotely. And we also have another product which processes streaming data in real time. So I'm going to today discuss about our architecture, the client-server architecture, and what's a distributed database cluster, and what are the communications the client performs, and why did we need an open protocol, what are the message types, and what's the backward compatibility from the client's view. And I will then start discussing our implementations, version 1 and 2 of the protocol, and the lessons we learned from while switching from version 1 to 2. And I will also describe some specifics to the protocol, and I'm going to talk about how we used code generation to generate the encoders, decoders for the messages, and what are the lessons we learned, and what we should be aware of when developing these clients for distributed environments. So our architecture is a typical client-server architecture with a number of servers forming a cluster, and we have many numbers of clients accessing these servers, retrieving the data from the servers. We distribute the data to the members, to the servers, using a partition logic. So each key we put onto a server, and we find which server to put based on a hash of the serialized key, and find which partition it matches, and we put it there, and we retrieve it from there. And partitions are distributed among the servers in an even manner, and we follow the updates of this distribution as a client. We have to support clients in different languages, so they have to interwork with together in the same cluster. It can be Java, C#, C++, Node.js, Python, Go, and another possible client. Our main protocol is a connection-oriented protocol, which is TCP/IP, which makes the things a little simpler compared to UDP with delivery guarantees. And we have to be scalable. We have some production environments where there may be thousands of clients. So these clients needs to be able to scale and fast. So a cluster looks like this, a typical cluster. So we have a different version different language clients, and they all work with these servers. They form a cluster. And these P1, P2, P3, and all these are the partitions. So server 1 only owns partition 1 and 2. Server 2 owns partitions 3 and 4, and so forth. And for simplicity, I did not represent here the backups of these partitions, and there's always backups stored in another server. So partition 1 backup will be stored on, let's say, server 2, and so on. Now, our communication from client to server is based on TCP/IP, connection-oriented protocol. We always initiate requests from client to server, never. This is for load distribution and for performance, because servers are pretty busy. We don't want them initiating their requests to the clients. We have to support authentication and security. And we have two types of communications. In one type, our client is smart and it connects to all servers in the cluster. And in the second, our client is a unisocket client where it only communicates with a single member. This may be a requirement in some production environments that they will not allow to connect to multiple. Now we have to design for the least amount of work on the critical path, which is the IO thread in our case. We have to do a minimum copy on the critical path, so minimum memory copy. So why do we need an open protocol? Because we have to standardize the protocol and publish so that other users can develop their clients on different languages. And also, once we publish, we don't let any breaking changes. So if we don't officially publish it, it's very easy that we insert some custom breaking changes, and we will not realize this effect on our clients. So we have to be very careful about it. And also, just don't forget that whatever message you design, there will be always requests to add some new features, and you have to somehow allow extending this message without breaking compatibility. So why do we need a backward compatibility? Because we have environments where we have different version clients running in the same environment, in the same cluster, and they all need to be able to talk to each other. They can be older clients, newer ones, or same version clients with a server. And it's also important that we can support a zero downtime during upgrade. So we can put in a new client with a new version 3.12, and just it starts working with the older cluster and older versions without taking the system down. So this is very important for our customers. And also, let's say that the new client has a new feature implemented. It has a new message type. The older clients will just ignore these message types and still will work without that new feature functionality. So they work together, but using the old features only. Now we have three message types that we talk to the server. We have a request that client sends to the server, and client receives a response message from the server. And an event message is the third message type, where once we register for a message, the server we'll keep sending the updates to that message to the client as there are updates. And these are called events, special event types. And we always correlate these messages with the correlation IDs. Correlation ID we keep is 8 byte, which is pretty big for the life cycle of the client. And so each message is unique. Our current repository supports around 377 message types. So it's also a challenge to keep all these messages in proper format and add the encoding and decoding capabilities to them. So we need some kind of automation there. When we first started designing the protocol, so we had some researches and we came up with this version 1 definition, which is we define the fields of a message, the name of a message, the fields of the messages, and also the metadata. Is it a retrievable message? Is it what's the message ID, unique type ID? What's the response type to this message? And name, address, and callable. These are the parameters that we send from client to server, and the name of the message is submit to address, for example, for this example. And the response type is specified here, so we know the type of the message we receive. In the first format, we have a header followed by a payload. Header is 22 bytes, so it's header is 22 bytes. It has a 20 bytes fixed part and 2 bytes that indicates the data offset. In the 20 bytes header, we have a size, frame size of 4 bytes. We have version, flags, type, correlation ID, partition ID, data offset. Now here, in most protocol designs, we always see the size and usually the version and a type, for example. Now, this 4 bytes frame size has a limitation. Due to this 4 bytes representation, we cannot go beyond 2 gigabyte of payload size. So our payload size is limited to this number. And also, I want to emphasize here, we use flags for fast processing in the IO thread. So we mark the message type event with a single bit, and we deliver it from IO thread to another thread for processing if it's an event. So we have a shortcut. So we need such shortcuts for performance. Now, the protocol version 1 had these problems. The first one was a significant one was a message length payload limitation of 2 gigabyte, which was not good because we could not, some customers may have a number of entries. Each entry may be pretty big, let's say 1 megabyte. And if you have many of them in one response, we cannot handle the total size greater than 2 gigabytes. And also for some we had some custom fields, for example, an address field that has an let's say IP number and a port number, but we want to add another flag to it, okay, another field to it. If we add, and this is used inside let's say middle place of a message, if we add a new field, it will break the compatibility of the older clients. So we did not have a capability to add a new field to this custom field. And also we had this dependency between code generation tool and the main project. So we had to release the code generation jar before making a release in the main repo, before using it in the main repo and sending a PR. So this was a kind of limiting factor and a bad developer experience. Now, how do we solve this with a new version protocol? So we decided we don't put the total frame, total message size limitation. We don't want to put it. So we don't want to have a limit. We want to represent the message even if it has more than 2 gigabytes. So therefore, we separated the message into frames. Each frame has a header and a payload, and each frame length can be up to 2 to 32. It's represented by 4 bytes. So we can have a pretty big frame, but we don't. This is not the message. So the message can have multiple frames, and it can be unlimited. So how do we achieve this? We use some special flags, and one of the important flag is final flag. So for all the frames except the last frame, this is set to 0, meaning there are more frames to come. And for the last frame, we know that it is set to 1, which indicates the message is completed. So once we see this flag, okay, we say message complete. So we put together all the frames and deliver it as a message. And here also there is this field, begin data structure and data structure fields. It indicates the begin and end of a structure, for example, a custom type, for example, an address. So in this case, we can design an address that's extendable. We can add a new field to it and do not break compatibility. We still have the event flag here for shortcutting the events. Now, also we changed the definition of our requests in our version 2. In the first one, we used here we used Java notation, and it was a simple Java method representation. And in the version 2, we use YAML definition, which is more extendable and which is more clear. We define the method ID, name, the parameters, the response parameters, etc. So we also use this YAML format for custom types such as address and stuff. And we have a way to verify these YAML files against the schema, so the user changing the message obeys our rules. Now we have, of course, in each protocol we have to have a set of built-in supported types, such as primitive types, Boolean byte, where we know the exact size in compile time, and variable size fields, their sizes vary depending on the data. This may be string, this may be a byte array, and some lists. And also we have some custom types which are reusable elements in the message definitions, such as address, member, and stuff. Now, for the custom types, we indicate their start and end by delimiter frames, which are just 6-byte frames, which only have a length and flex field set, and the frames in between represent the actual fields of the custom field. So this way we can always add a new frame in the middle, and new frame before the end frame, but we always add it at the end. so that a new field can be added. An old client will read up to that frame and skip the rest until the end frame. This allows compatible working of the old and new clients. And this also gives us an opportunity to design custom message inside another custom message. Each are delimited by start and end frames. Now, if you have a list of entries, how do we encode it? Okay, if it is a primitive type, a simple, let's say, integer of list of integers, it's over costly to use begin and end frames logic. Hence, we have this optimization for fixed types that we put them into a single frame, one frame, and we just encode it after the header part. Okay. But for variable size types encoding, we use begin and end frames. Okay. And we encode each element as one frame. So this way we can achieve represent a list of variable size. Now, new protocol characteristics are we have an IO thread, which is the most important thread we have. It only knows simple frames. It only knows how to read frames. It reads the frame length followed by flag fields until it sees the isEnd bit set on the frame. So it does not do any processing at all, just reads and accumulates the frames. And message fields are either fixed size or variable size, right? But in the protocol design, we always send the fixed size fields first at the first frame. This is for better design because with this design, at compile time, we can know exactly which offset to see which field. And then we put the variable size fields after the fixed size fields. And we use begin and end frames for arrays and for custom types. And we have no payload size limitation, and the custom types can be extended without breaking compatibility. Now, let's look at how do we generate all these messages. We use the tooling, of course, very important. In protocol version 1, we use the Java compiler annotation processor. In protocol version 2, we use the Python code generator Jinja. So what are the pros and cons? The Java compiler annotation version 1 had a cyclic dependency between the projects, protocol and main repo, cyclic dependency in terms of releases, and so it was difficult, bad developer experience. The developer had to have the protocol jar released before he can send his PR to main repo. In version 2, it's just we use the code generator project just as a tool. So the user changes the YAML files, generates the codecs, and sends his codec changes together with his main repo changes to the main repo, which is the Hazelcast repository. So he doesn't need to wait for any protocol jar release. And but how do we control any breaking changes? We add extensive tests for checking these changes. So the user does not change the generated code by hand. So we use a checksums there. So we have to put these in the first place, these checks. Now, what's the lessons learned? Okay. Now, first of all, we have to know our domain. Okay, we have to optimize for the common case. For example, what is your key data usage pattern? Okay, we have a key value pairs, for example. We have to eliminate the memory copy for the common case as possible. And we always aim for the common case. We have to send or process the fixed size fields first because they can be known in compile time. When writing logs, please do not use cryptic debug logs. Just put the human readable formats. And don't forget, when you design a protocol, it will always change. You cannot design it and say, okay, this is it, and I designed the best protocol. It will never change because of the products you and the users you have. You usually need some extensions. So make the protocol extendable from the first, from the design. And have these mechanisms in place, and but make sure that they cannot be broken. It can be with compatible tests. And make sure that whatever you design, the types you come up with are can be supported by different languages. So don't make it language specific. For example, an enum type. It's represent different in Java, in C, in C#. So a common subset will be using an integer, okay? We have to develop simplify developer usage experience. So our users, our protocol users are actual product developer, and we have to make it easy to add a new message, extend any existing messages he uses, and so we always have to provide automated code generation because developers always need to tend to take shortcuts, and they tend to, of course, in these shortcuts break compatibility. So just put in some precautions, some tests to protect against compatibility breaking. Put in unit tests to cache them. We have a code owner feature hook into the repo so that any protocol related change requires a review from our team. And the generation tool should not introduce any cyclic dependency. It should be just a simple generator. And yeah. Now we always need the test against performance. So we have to do some repeatable, put together a repeatable performance suite test so that we can measure the design effect we have on the performance. Theoretical assumptions usually become false when the overall system is being tested, the performance. We have to look at the big picture and analyze which places the most processing is spent and try to optimize there, and optimize the stages where they have the highest latencies. What are the some performance tips? For example, do not change allow too many thread changes in the hot path, in the busy path, because thread scheduling is costly and it decreases performance. The deallocation of objects is costly, so do not create too many objects if possible. Minimum liter, it means minimum liter if possible. And we had an example. In first implementation, we used a simple language provided list of frames, and we observed that there were too many object creations, too many liters. So then we implemented the same list with a simple next pointer based implementation, a very simple implementation which decreased the litter significantly, and it also affects the performance. It increased the performance with this simple change. And this is it for me today, and you can get more information about our project, the protocol project, the generator, and details from these links. Thanks for listening.
It was a great speech, very interesting, highly technical, I would say, but I enjoyed it, and I think the rest of the people, the viewers, also did. And we have actually questions, and let me start with a question regarding the young developers. Uh, why do you think open source coding is important, and how would you try to convince developers starting their careers to get involved in open source projects?
Well, open source is of course important in the way that it's accessible to everyone in the world, and the products, the libraries you develop can be used worldwide, and you can publish it to everyone. Everyone can review it. So they are usually tend to be more stable, more reviewed, and also you can also observe what's expected from the community. If you develop a wrong product, you will get the signs from the community that you are in the wrong direction and you can change your product. So it gives a feedback loop, and that's very valuable for us. And for young developers, I certainly, I mean, I like everyone to contribute to all these open source projects, and we always promote it via Hazelcast projects, but they get a chance so that their code can be integrated into the product and used by a lot of people. So I think that that's great for anyone who is starting, and also even for experienced people, right? So you see your code used everywhere, integrated into different projects, and that makes us happy, you know.
Yeah, and we see it's making a big impact now. Open source projects are developing everywhere, right?
Yeah, I mean, there are a lot of companies open sourced a lot of their closed products, and one of the biggest is Microsoft. Was well known for its closed source, but now most of its projects are open source. So it's a way to go. I mean, there's no alternative because there are a lot of competitors with open source and stable products. So, and yeah, I have been always on the support of open rather than closed. So, yeah.
I hear you. Excellent, excellent. Okay, I have another question here. The question goes, are the languages you refer to in your presentation the ones you use or accommodate, or there are more?
Yeah, these are the languages we currently use and also officially developed in Hazelcast. So if you want to use Hazelcast, you can use from all these different languages, and we have to make them ready for the community to use in their products. But these are not the only products, only languages to use Hazelcast, because we have our protocol as open protocol. So we published it, and all the rules, all the data formats are ready. So anyone can write in their own languages. And we see from community some adoptions. For example, there's a Rust client. Some people from the community just developed it. There's a C client. So, and we always want to increase this number to other languages as well. So the main reason of designing an open protocol was, in the first place, adoption of these different languages, because we only have limited sources so we can only provide certain languages, which are the mostly used ones usually. But there are a lot of other great languages that can be integrated via the community. So anyone can look at our code, our published protocol document, and write their own language client. So yeah, it's always extendable. Yeah.
Okay, we have more questions coming. So okay, if you're ready, there's another one says, is it ensured somehow that each message is broken to the optimal amount of frames so there are no excessive frames? That's kind of technical, but I don't know if you want to.
Yeah, I mean, I want to point, and it was also in the presentation, that we always have to optimize when we do a protocol, because the binary sizes on the wire makes a lot of difference when you want to design high performance, right? So you want to minimize as possible, but also don't make it too cryptic. And one of the things we do is we always put the fixed size fields, which are the sizes we know at compile time, in the first frame all together. So all offsets, everything are known at compile time, and it's only one frame. So we don't want to make too many frames, of course. And the second thing is, for example, array optimizations. Okay, if you have an array of very small types, like an array of byte, array of integers, and these are very common, you don't want to put them into multiple frames because each frame has an overhead of 6 bytes already. So for only transmitting 1 byte, you cannot get that. So we put all of it in one frame. So we have optimizations like this, and we have to do this. And but other places we cannot do this. We use begin end frames and more frames, of course. So there are limitations to where we can make optimizations.
Great. Another interesting question, since we have a short time, can you give us an exemplary use case where Hazelcast excels? You know, since this is what you work on, you have a good understanding of that.
Yeah, I mean, you know, Hazelcast is a key value store, actually, in simple terms. So when you want to speed up your application, it can be a web application, it can be a banking application. You load all the data into memory once, and then you just access it from the RAM. So it's a lot faster than accessing it from disk-based storages, databases. That's why you use it. It's a cache solution, actually. So it may be a web caching, or it may be caching in other places. And it works very simply with key values. And there are other features it has, but mostly these are mostly used features. You can also have, execute your runnables in multiple machines and return the results. So you can also do things like this because we provide the distributed environment, execution environment. So these are kind of use cases. Yeah.
Excellent. So Ihsan, thank you so much for being with us today. Really hope that in a future event you'll be able to come and visit us as well. We really appreciate it. This was a very interesting presentation, and the audience enjoyed it. We had so many questions. Thank you so much again. Yeah. Have a great night.
Thank you very much for providing this opportunity. It was really great, and my first online experience on a conference, and it's really going good. So thank you.
Excellent. Thank you so much. Take care.